So, in this lecture we will talk about alpha decays and other decays which involve strongly interacting particles such as heavy ion decays such as carbon 14, 28 silicon decays apart from alpha decay of course. Then we will talk about spontaneous proton emission, spontaneous 2 proton emission. We have not yet found any evidence for spontaneous neutron emission, but there is no reason why we should not find it in the future. And finally, we will talk about spontaneous fission. So, this shows a cartoon here which is just sort of illustrates the fact that there is a difference between how classical systems behave and how quantum mechanical systems behave. So, here is a line. Of course, this does not happen really on that scale. However, this is just the cartoon just to illustrate what could happen. So, there is a lion standing on the other side of the wall and a human being here. So, he is perfectly safe, he has no problem. But where the lion to tunnel through the wall, then of course there is a big problem. And this depicts the situation where the lion can tunnel through the wall. Okay, so first of all, let's look at the energetics in alpha decay. For a nucleus A to decay into B plus an alpha particle, of course the energetics has to be right. In other words, the Q value, which is for alpha decay, Q alpha, has to be greater than 0. What is this Q alpha? This is just the masses of A and the difference between the mass of A and the sum of mass B and mass alpha. Okay. So, there are tables which are there in literature which actually tabulate the binding energies. So, the binding energy of the alpha plus the B has to be greater than the binding energy of the A. So, this has to be greater than 0. Actually I think there is a sign missing. Okay. So, I think I'll check this sign out. Basically, the mass difference between the left hand side and the right hand side has to be greater than 0. Okay, and this is tabulated in terms of binding energies which you have, and so I hope this sign is correct. Otherwise, this has to be just the other way around. The kinetic energy of the alpha particle is given just by the Q value for alpha decay, which is typically between 4 and 8 or 9 MeV or so, and the ratio of the mass of the B divided by the mass of the A. Okay, so sorry, this is again, yeah, this is right. The T alpha is just the ratio of MB by MA times Q alpha, and this is just A minus 4 approximately, A minus 4 by A. Assuming that the binding energies for A and A minus 4 are similar, then this is just this ratio, which is of course close to Q alpha. Okay. On the other hand, the recoil energy, which means the energy taken away by the recoiling B nucleus, that is about 4 by A times Q alpha approximately. Okay. So, if you have a Q alpha of let's say 5 MeV and a nucleus 240 which is decaying, the daughter nucleus, which is A equal to 236, takes away a small amount of energy, not very close to 0, it's about 83 keV. So, it's in principle measurable with detectors which have resolutions which are better than this. Okay, so the energy released in alpha decay for heavy nuclei, so called Q alpha, this is plotted here as a function of A. I have taken it from a reference and I'll give that later in the PPTX slide. So, as a function of A for the heavier nuclei is plotted from 200 to about 250, and you can see that there is a peak at about polonium 212, because then that emits an alpha and goes to lead 208, which is a doubly closed shell. It has a closed shell for protons, Z equal to 82, and a closed shell for neutrons, N equal to 126. So, that is the peak. So, this is around 8.8 odd MeV, and then it again decreases, and then there is an average of between 6 and 7 MeV for all these heavier actinides. The alpha separation energy versus mass, and this is plotted right from 0 to 250. So this alpha separation energy is somewhat high in the light masses, but then as you increase the A, then of course because of the partly because of the Coulomb energy, this sort of decreases, and in fact for some nuclei like in this region, heavy region, it in fact the binding energy even becomes negative. So it means it can spontaneously decay. Here you have to supply energy to the nucleus for the alpha to come out, whereas here it spontaneously decays into alpha. Of course, the decay probability depends on, of course, very heavily on the binding energy and the Coulomb barrier that it faces. Okay, so the typical alpha nuclear potential is like this. I have not shown all the way down, but it'll be of the order of 100 MeV or so deep. And so what is plotted here is potential as a function of distance between the center of the alpha. Assuming I mean many of these the formulations that we have assume the radius of the alpha to be in fact approximately 0. Of course, you can put in a finite radius and then and so on. But essentially, there is a strong nuclear potential at short distances of the order of the radius of the nucleus, and then it increases because of the Coulomb potential, and then there is a barrier. So this is the place where the Coulomb and the nuclear interaction sort of play a roughly equally important role. Coulomb winning slightly. So then that is of course here where it becomes 0, but then it increases at larger distances and then falls off as 1 by r. Okay. So classically, if you have an alpha particle which is E greater than 0, but less than the Coulomb barrier, which is this Vc, then the alpha particle, I mean, in principle, it cannot escape. So this is a mistake. I think classically, alpha particle, it should be cannot escape. However, if it is as it is actually a quantum mechanical system, then of course you can have an alpha particle come out, and that's the so-called tunneling that the alpha particle can do. And this problem was first solved by George Gamow in 28, and almost simultaneously by Gournay and Condon. Separately, they didn't know that Gamow was also working on this using the newly developed quantum mechanics. So the quantum mechanics was developed in about roughly 1925 by Schrödinger and independently by Born, Heisenberg, and so on. And Gamow and Gournay and Condon were the first to use this to actually look at the spontaneous alpha decay. Let's say you have a alpha particle here, then this has a rather narrow width, sharp alpha, whereas if you have something like this, then this has a the width increases, and this keeps increasing with energy. In fact, the width of the state inside the nucleus actually increases considerably, and around the Coulomb barrier it becomes the widest, and then this increases only slowly thereafter. So these are called quasi-stationary states, because of course a state of alpha in the well cannot live forever. Depending on what its energy is, it will escape, and then it will escape to infinity. And the probability that it escapes to infinity will keep increasing with the energy of the alpha, from below barrier to near barrier, and then of course above barrier. There is an approximate way you can solve this problem by doing a very simplistic approximation that the alpha is in the potential well of the nucleus, and then there is a square barrier, and then if it has an energy E, then it can tunnel through this square barrier. This is of course a very naive kind of approximation, but nevertheless, just to see what it leads to, it's a useful exercise. So if the wave functions psi 1, psi 2, psi 3 are there in regions 1, 2 and 3, then the psi 3, that is the wave function outside, which of course goes to infinity then, divided by psi 1, which is the wave function inside, squared, the modulus squared, this is actually proportional to an exponential of minus g, where G is has a square root dependence on the difference in energy between the barrier and the energy of the alpha in the inside the first the well. And of course, this means that this is not a stationary state. In the time dependent picture, this psi r of t can be written down as psi of r exponential. So you have a IET normally, but you add a small imaginary component to that, and then minus sign indicates that it's actually leads to decay of the system rather than growth of the system. And so if you square this, then the psi of RT, the modulus squared goes like psi r squared times a exponential minus gamma t by h cross. Okay, so h cross by gamma in fact can be also be written down as tau, the lifetime of the state, and so basically it is exponentially decaying wave function with time, and that tau is just the lifetime of that nucleus with respect to alpha decay. So a more realistic view of this would be, of course, this is still not completely realistic, but at least it's a more realistic way of trying to estimate this. That is by assuming a kind of a deep well, and then from a radius of r, then only the Coulomb potential operates, which means that it dies as 1 by r. Okay, so if an alpha particle here, then the wave function, of course, there is a wave function here, there is a wave function in the barrier, and there is a wave function outside the barrier. So similarly, then using the WKB approximation, one can estimate the modulus of the wave function outside this turning point and inside psi 1 here, psi 2 as I said here, and psi 3 beyond. So the square of this modulus can be estimated, and so this is just this term exponential some fraction here, an integral from r to b of a certain factor, but that depends basically on the q alpha. Okay, so this exponent for these approximations where q alpha is much less than Vb, this is usually the case. Suppose you take this to be 5 and the barrier in A equal to 200, 240 nuclei, that's of the order of 20 MeV or thereabouts. So this fraction is typically about 0.25 or even less, and so this is true, q alpha is less than Vb, and for r, which is less than this turning point, so then this exponent leads to a tunneling probability, and then using the barrier assault frequencies, how many times this alpha hits this barrier back and forth, then you can calculate the decay rate of this wave function. So V in by R times P. So R by V in is the number of times the time scale of that, and then inverse of that is the frequency. So that frequency times the probability of tunneling. So this should actually be tunneling. Then you can calculate the decay rate, and then from there you can get a half-life, and so the half-life can be estimated to be from this relationship 0.693 by the decay constant. So log T half is just A plus B times square root of Q alpha, and this is in fact known as the Geiger-Nuttall law, which was empirically derived by looking at systematics of alpha decay in the earlier part of the last century, 1911, 1912, by Geiger and Nuttall. So this is an experimental plot of the logarithmic plot of the partial half-life in seconds versus the alpha decay energy. Okay. So as you can see from the previous slide, this, if I plot log of t, then this should go like 1 by square root of q alpha, and in fact this seems to be roughly obeyed by the systematics here. So this corresponds to a second, this corresponds to a year, because of course as you see there is a huge range in the lifetime. So you can go right from 10 to the 22 years to fractions of a second, even in something like a nanosecond, 100 nanosecond or so. And so this is sort of it follows the systematics that you expect. Of course, there is variations because it depends on the structure of the nucleus eventually, and what is the preformation probability and so on. So that we'll see in the subsequent slide. So there are three parts to this. There is the formation probability of the alpha, and the alpha particle actually, through experiments of knockout reactions and so on, it actually survives for a relatively longer time on the surface of the nucleus. It can be, of course, formed in the interior of the nucleus, but then nuclear collisions dismantle the alpha, and so it forms for a while and then breaks up. However, in the surface, this exists for a slightly longer time because the density of nucleons is lesser and the probability of collision is therefore lesser. So, the one point in estimating this is that you have to know what is the formation probability of the alpha particle. Then you have to take into account the effect of the orbital angular momentum of the emitted alpha particle. Of course, the S wave is the best because then it doesn't face a barrier due to the angular momentum, which goes basically like L into L plus 1 by R squared proportional to that. And then there are, of course, nuclear structure effects. If you have nice alpha clustering in these heavy nuclei, then of course you expect more alpha decay. And so in this case, for instance, you see the reduced width for alpha emission. This is basically takes out the statistical factors. Then you can see that in this region 202 to 218, there is this, of course, note that this is a logarithmic scale, so it decreases to 210, but then when you go to 212, because then you can decay to 208 lead 208 nucleus, that it increases, okay, and then it stays like that. So this is of the order of 10 to the minus 1 or greater, which means that 10% or more is the kind of reduced width that we get for the even polonium isotopes. Of course, such numbers exist for other nuclei as well. The effect of finite L, which means L not equal to 0, of course, leads to a reduction in the probability of getting out an alpha, the tunneling probability for the alpha. And that's just because you have a barrier which is slightly more, corresponding to L into L plus 1 by R squared. This, of course, decreases a little bit faster than the Coulomb potential. So, this is the Coulomb potential plus the centrifugal potential as it is known, and so this goes like 1 by R, this goes like 1 by R squared, and so you can see that the decay rate or the decay constant is 1 for, let's say, if you normalize it to 1 for S wave, L equal to 0, then it becomes 0.7 for L equal to 1, but as small as 0.037 for L equal to 4, and this is for nucleus which is around 85 and the Q alpha is around 5 MeV. Okay, now you can also have, just like you can have alpha emission, this is the most prevalent, of course, but you can also have something called the heavy particle emission from nuclei, and this was seen by several groups, and of course was studied in smaller detail by many groups. The French group at Orsay, then there is a group in the US, and of course a group in UK. So the first such measurement was carried out by Rose in 1984. He saw evidence for carbon-14 emission from I think it was radium 223. Yeah, here it is. And so actually this is also a typo. This is actually not a track detector. This is a delta E gas detector. Okay. So, and then subsequently there were experiments done by, as I said, by the Orsay group. They used a solenoidal magnet to transport the carbon-14, or they also did later experiments on silicon-28 decay, and onto a detector, so that the alphas are de-emphasized, because primarily the nucleus like 223 decays by alpha, and this is an extremely small branch of the order of 10 to the minus 10, minus 11, 12 and so on. So, and then of course you have a delta EE detector, because now you don't have all those alpha particles coming and hitting them, only a few of them, and therefore you can afford to use a silicon detector. The Rose and Jones, they actually employed a silicon detector, but then they found that the alphas are actually there's a lot of irradiation on the silicon detectors, and that leads to a degradation of the silicon detectors. So they ultimately used a gas delta E telescope. Similarly, there are other experiments on radium-226, and there's a nice review article in '89. But of course, there are subsequently experiments done also using this same soleno magnetic transport systems and so on. So this figure actually shows the data from the Nature paper of Rose and Jones. So the total energy is shown here. You expect from the mass tables that you should have carbon 14 emission at around 30 MeV or so, and indeed they see a bunch of counts here in that expected region. So this is the carbon 14 region that they expect. And so, as I said, they use the delta EE, and so you can add the delta, you can add the energy in the first detector and the second detector and sum it up, and then plot it against the total energy. And so you don't see any counts elsewhere, except for two crosses here. In fact, one of them they could attribute to lightning, and that hit that affected the mains supply, and so there is a big signal that came through the mains onto their preamplifiers, and so this was actually not a real signal. So this was due to lightning hitting the mains somewhere. So you see that in very low counting experiments, such backgrounds are also important. There could be other backgrounds, for instance, and then you would have to take care of them, such as let's say some big power device being switched on that leads to a signal coming through the mains into your preamplifier and mimicking a signal that you actually want to measure. Okay, so this is again data from the French group, Urani et al., where they see even fine structures. So you can see that in the early experiments, you just had a few counts, 5 to 10 counts. Now here you have a spectrum. I mean, you can see that this is carbon 14 decaying to the ground state in lead 209, carbon 14 decaying to the 780 keV state here, and you can see the number of counts here. I mean, there are something like about 200 counts here, about maybe 50 counts here. So there's huge statistics. So they counted. They also had very strong sources, of course. Okay, this should be this is a small typo. This should be carbon 14. Okay, and this is another experiment where they just observe one count from actinium-225. So this is a very rare decay that they have observed, again using Soleno, and this is reported in 2001. Okay, now we come to, I should have also, I did mention that there are also cases of silicon-28 spontaneous emission from sources. I have not given a figure here corresponding to that. You can look it up in the review article by Price. Okay, now we come to spontaneous proton emission. Now, the protons, for instance, we don't have too many cases of, or actually no case of commonly available radioactive sources that lead to spontaneous emission of protons. On the other hand, for alpha particles, we have many. In fact, we have even naturally occurring isotopes, and then you have their decay chains coming up. So you have plenty of things in between which can be extracted from uranium or thorium ores and so on, and these emit alpha particles. In the case of protons, you don't have this situation. So for spontaneous proton emission, of course, you need to have very proton-rich nuclei, and that is not usually available in nature. So this was first discovered by Jackson in 1970, and then it was discovered in 53 cobalt. So the excitation energy was 3.2 MeV, but subsequently there are plenty of these that have been found, and the most well-known example is 151 lutetium, and in fact what is plotted here is the half-life versus the Q value. You can see that this was emitted with an energy of about a little more than 1.2 MeV, and this fits best if you have a L equal to 5. So, if you want to have a long-lived proton emitter, which makes for better experiments, then there better be also a L barrier. The proton, of course, has a barrier which is half for the same nucleus, Coulomb barrier, I mean, as compared to the alpha, Z equal to 1 versus Z equal to 2 for the alpha. But then, if it has to survive for some time and then enable you to detect it cleanly, an L barrier also helps, and in this is a nice case where L equal to 5 fits the data best. This is the reference given here. Further, people have also seen cases of 2 proton decay, and this is in 45 iron. This is a very proton rich nucleus. Remember that the naturally occurring isotopes of iron are, I think, 54, 56 and 58, whereas this is proton rich. So, if you have 26 protons in an iron nucleus, then you have only 19 neutrons in this. So, the number of neutrons in fact fewer than the number of protons. So, this is very close to the so-called proton drip line, which I might have mentioned earlier. In case I have not, the proton drip line is just something where the separation energy of the proton becomes 0. Okay. So, if you go to even more proton rich nuclei, then the separation energy is in fact negative, and then of course you can it can emit protons with a lot of probability, large width for proton emission. So, this is a schematic for this case. This was first found in 2011, where they used a very novel kind of detector, a ionization detector, but also it had a gas which actually scintillated. So, they actually had a camera which took photographs of this, and also it is a fast camera, so you could see the time sequence as well, and then there was a recording system. So, the incoming ion came in from, let us say, a mass separator, then it stopped in this ionization chamber. It led to ionization, which of course got multiplied, and so you got a fairly large signal, and that the multiplied electrons also cause ionization and excitation of atomic levels. So, this actually gas had helium, argon, and I think methane, and so you can, as I said, this is a novel idea proposed by Georges Charpak, the Nobel laureate, who actually invented the multiwire proportional counters, large area multiwire proportional counters, and drift chambers and so on. But he has contributed to lots of novel ideas in particle detection, and so they use this Charpak method to actually image it. And so that is shown in the next slide. So, this heavy ion comes in through this 45 iron, and then it decays into 2 protons, and the energies, the intensity of the proton emission is shown as a function of time, and this is the reference 2007 Fitzgerald letters, and they recorded about 125 events. So, the half-life towards spontaneous proton emission was about 1.25 with about 10 to 15% error bar. From the energy angle correlations, and this showed that this was actually a 3-body decay and not a 2-body decay which involves the diproton, which was a prediction of Goldansky way back in the, I think, 60s or something like that. So, by 3-body I mean the initial 45 iron nucleus decays to a nucleus which is 43A and Z equal to 24, but it also has 2 protons in the outgoing channel. So, that is 3 bodies. Okay. So, now these protons of course can come, the contribution can come from various orbitals in iron 45, and they figured out that this is about 24% contribution from the p orbital and 76 from the f orbital single particle states in the shell model picture. So, anyway, they showed that this is not a diproton emission, but rather a 3-body emission. Now, is there 1 neutron or even maybe 2 neutrons spontaneous emission or not? Well, we do not have any experimental proof of that yet or evidence of that yet, and so this is actually an open problem. So, maybe in the near future we will find cases of 1 neutron or perhaps even 2 neutron spontaneous emission. So, now since the neutron does not have a barrier from due to the Coulomb potential, is neutral, electrically neutral, therefore the only barrier that it can have which can sustain this for a long enough time for it to be observed would be the let us say a L barrier, okay. And so assuming that you have a D wave, then in A equal to 25, for instance, you could have emission of up to, so this is for proton emission of course, but you could have such emission from 25 oxygen in principle. 25 oxygen has 8 protons and something like 17 neutrons. So, it is close to the drip line, but this time the neutron drip line. But you have to have a barrier, as I said, for it to be detected nicely. So, if you have something like a D wave emission, then this would be having a width, the energy would be just less than 1 keV, but this is in principle possible using time of flight methods. So, such fine tuning is probably difficult to get in SD shell, but perhaps in F and higher FG and such higher shells, maybe such a thing is possible. So, anyway, we do not have yet evidence for this, but this is an open problem, as I said. Now, let us just look briefly at spontaneous fission decay. Of course, thermal neutron induced fission of uranium was discovered by Hahn and Strassmann in 38 through the radiochemical separation of the products, and they got very relatively light products as compared to uranium. They got barium and krypton, and then this was interpreted by Meitner, Lise Meitner, who actually had started this program of transuranic elements at Berlin, and she and Frisch figured out that this is actually fission. She in fact coined the word fission from the life sciences, that the nucleus just breaks up, and the theory for that of course was worked out by Bohr and Wheeler. Now, this was in neutron induced fissions where the typical excitation energies are 6 to 8 MeV, but you can also have spontaneous fission, and this was discovered by Flerov and his colleague in 1941 in U238. Interestingly, S. Chatterjee and his colleagues in fact had observed evidence in the Bose Institute by exposing emulsions and plastic detectors to uranium, and they in fact sent a manuscript to Science and Culture, but the editor, who was actually the director of this institute, thought that they need more hard evidence before such a very surprising discovery can be published, and so that got delayed. So, although they did the experiment and had a preprint 1 year or so or sometime before Flerov, but their publication came later, and so the discovery of spontaneous fission is attributed to Flerov rather than to Chatterjee. Okay. Polikonov in 62 discovered the fission isomer 242 metastable state in americium, and the excitation energy was about 2.2 MeV and the half-life was about 14 milliseconds. And this was very surprising, such a high excitation energy, but relatively long half-life. So, this was understood in terms of shell effect leading to a second minimum in the potential energy versus deformation parameter, and this was understood within the work of Strutinsky mainly because he had a liquid drop plus shell model approach, and that was accurate to a few MeV, and he showed that this is possible. And then of course subsequently, I mean, there was also work by Myers and Swiatek and so on. These are the references for the original fission, neutron induced fission. Okay, so these so-called shell effects modulate this otherwise smooth barrier that would be there by having another well in that potential barrier, and this is the so-called second well. So, this is the first well. The ground state is that already has a finite deformation, and there are states in this, and so if you have a nucleus sitting here, of course it can fission. It has to go through this wide barrier. So, it has a rather long partial half-life for this process. Most of these isotopes actually decay more predominantly by alpha decay, but there is a fission probability, spontaneous fission probability. But suppose you create a nucleus here, then the barrier it sees is much smaller, and therefore it can decay in a very short time. And so the experiment of Polikonov is the one here reported in 62, and then this was understood within these theoretical phenomenological models by Myers-Swiatek and Strutinsky. Okay, so in summary, we have looked at the tunneling of alpha particles through the barrier in alpha decay, spontaneous proton and 2 proton emission in proton rich nuclei close to the proton drip line. We have seen the spontaneous emission of carbon 14. Okay, I didn't show a figure on silicon 28, but this is there in that review article from actinide nuclei. I have not said about the neutron emission, we haven't yet seen it, but there is a possibility. In fact, some of the young people who might be listening to this might actually find someday evidence for spontaneous neutron emission. And then finally, we have talked about spontaneous fission. Thank you.